Momentum. What is momentum? Momentum is the product of the mass of an object and its velocity. It can also be thought as the tendency of an object to keep moving in the same speed in the same direction. Because momentum has a magnitude and a direction, it's considered a vector quantity. Let's apply this momentum law in an example. Here we have Jolson and we have Mr. Turtle. Let's say they're in a 100-meter sprint, and at the 50 mark, Jolson is traveling at 20 k's per day, and he is weighing 80 kilograms because he is fat. Here we have Serge at the 50-meter mark. He is traveling at 40 k's per day, and he weighs at 20 kilograms because he is not as fat as Joel. So who do you reckon has the bigger momentum, Joel or Mr. Turtle? Have a think. Did you pick Joel? Well, if you did, you are correct, because he has the bigger momentum because he is fat. Every second of our lives, we experience force. As I stand here, I am experiencing force. I can even model the forces that are acting upon me. But first we have to understand that force is a vector quantity. And also keep in mind the equation for force. Force equals mass times gravitational force field. So to calculate the force that is acting upon me, I multiply my mass, which is 54 kilograms, times the gravitational force field. And that adds up to a total of 592.2 newtons downwards. So what's keeping me from falling through the ground? Well, there is an equal force pushing me back up.
So there is 592 newtons downwards and 592 newtons upwards. Therefore, there is a net force of 0.
Now we have a look at Brad Sampson and Miss Altonzi.
G'day, mate.
Miss Altonzi will attempt to kick the ball at Brad, and Brad will block the ball. And here we will look where we can model the forces.
Here we can see the contact between Miss Altonzi's foot and the ball. We can see the force that the foot exerts on ball, but we can also see the reaction pair, the force that ball exerts on foot. We can see that the magnitude of these forces are equal in size. These forces are known as an action-reaction pair. What we see here follows Newton's third law. Again, we can model the forces that are in action. Here we can see the force that ball exerts on Brad, and the force that Brad exerts on ball. We can see that the force Brad exerted on the ball has caused it to come to a complete stop, and no longer accelerating forwards, but rather backwards. Though we can't see it, the force that the ball exerted on Brad has caused him to slightly accelerate backwards, but the effect is not as great compared to the ball, as Brad's mass is greater. Or is it?
Spit on the ball.
Hello, miss. I'm doing my presentation on Hooke's law. It is the law of elasticity. And that means that any object that is elastic can stretch harder if there is a force on it. And so I will show you a presentation. See this rubber band? Right now, there is no force applied on it. But when you apply force on it, it stretches. Ooh, that's right, it's cool. I know. Anyway, but if you apply too much force, I'm afraid of doing it, but ow, damn, give me a nail or something. Ow. I'm scared. So. And so I will put too much force on the rubber and it will be broken. See, Mr. Tonzi, how I broke it. That's because there was too much force on it and it could not handle the pressure. And so, this is the end of my presentation.